special program on general relativity for 2 days. It's part of the big program that we've been running this year in CMSA, Center of Mathematical Science and Applications. So we run the whole year on linear equations, and been very active. At the end of this special year, general relativity is the major field. Starting already for about a month ago, we have who has been running. Yeah, Phil has been running this special month on general relativity. Has been doing very well. Partially because we have been also working with the Black Hole Initiative run by Smithsonian and Astronomy Department. So we're going to work with them constantly. But these 2 days we are specialized majorly on mathematical aspect of general relativity. So I think we are doing well and on this program, and everybody was happy. Some people left already, unfortunately. But still, we have some hardcore people coming, and we are very happy that it goes well. We have some friend, our secretary, Sarah, who has been working very hard on this. So let's have Greg Galloway to start out the first lecture. So the title is Remarks on Photon Spheres and their uniqueness. But before that, we should thank Phil for working so hard on this program.
Thanks, ST and Piotr, for the invitation to participate in this workshop and to have an opportunity to visit this new center. So in Carla Sederbaum's thesis, she initiated a study of photon spheres in static spacetimes. And one perhaps expects that static spacetimes that contain photon spheres should be rather special. And this she quantified in her thesis. She proved a uniqueness result or rigidity result for vacuum static spacetimes that contain photon spheres. I'll be giving definitions in a moment. She proved this rigidity result and uniqueness result in this setting, which is analogous to Israel's proof of black hole uniqueness. And in fact, her proof is an adaptation of Israel's original argument. Carla gave a talk at a special session that Gilbert Weinstein and I ran at a meeting in Israel several years ago, and her talk and this material piqued my interest. And then in fall 2013 at MSRI, we began talking more about photon spheres and related things, and we ended up writing a couple of papers together. And in this talk, I want to discuss the proof of the following theorem. Again, things will be defined as we proceed. So we consider a static space-time, so n bar, r cross m, with metric g bar minus n squared dt squared plus g, where n is the static potential. It's a strictly positive function on m. And throughout this talk, just for concreteness, I'm going to assume 4 dimensions, although many things I talk about will hold in higher dimensions. And see the first typo. Assume that our static spacetime satisfies the vacuum Einstein equations, that the spatial part m is asymptotically flat in the metric g. And also for simplicity, we're going to be assuming just one asymptotic end, although I'll say more about this later. And that the static potential goes to 1 at an appropriate rate on the end. And furthermore, we suppose that M is a manifold with boundary, whose boundary consists of photon spheres. Then the conclusion is that the static spacetime is isometric to the region r greater than or equal to 3m in Schwarzschild spacetime. In particular, the boundary is connected. So this generalizes Carla's original result in that it allows multiple photon sphere boundaries. And another nice feature of this is that from a certain point of view, the proof is really simple compared to running adapting Israel's original argument. So here's a brief outline of the talk. We'll start with some basic definitions and some general properties of photon spheres, both local and non-local. Then we'll talk about the proof of the theorem and discuss generalizations as time permits. So I'm introducing some terminology that's been used in the literature. By a photon surface in space-time, in a space-time m bar g bar, we mean a time-like hypersurface. Hypersurface is induced metric is Lorentzian, which is totally null geodesic. That is, any null geodesic of P is a null geodesic of space-time. Or equivalently, if you go to a point in P and look at a null tangent vector at that point and look at the ambient null geodesic in that direction, that null geodesic stays on P.
Correct?
Yes.
Are you assuming compactness or something like that, or
On
smoothness? or
cross
vividness?
sections or anything like
Yeah.
that, everything's smooth, and for this definition, I'm thinking compact cross sections, but not requiring it at this point.
But you're well with the
Yes.
theorem.
Yeah, exactly. Perhaps the simplest example are these so-called pseudospheres in Minkowski space. These are these hyperboloids of revolution, and in fact, you can see in certain books these hyperboloids of revolution being ruled by null lines. So in fact, the entire region outside this null cone at the origin is foliated by photon surfaces. But there's a simple fact that's perhaps not so well known that convinces me that these examples are in fact photon surfaces. It's the following: a time-like hypersurface, I should just say time-like surface here because that's part of the terminology. A time-like surface P in time-like hypersurface P in space-time m bar g is a photon surface if and only if it is totally umbilic. That is, if and only if its second fundamental form is a multiple of the induced metric on P. It's a very simple argument using the fact that the second fundamental form measures the difference between the ambient Levi-Civita connection and the induced Levi-Civita connection. So this is a simple characterization of photon surfaces, and the earliest place I've seen this observed in the literature was this paper of Ellis and Pravati. So photon surfaces are time-like hypersurfaces which are totally umbilic. And now we move to the definition of a photon sphere, which we'll be defining only in static spacetimes. So we consider a static spacetime m bar g bar, and let sigma be a closed surface within space m, which we sort of think of as the T0 slice in the static spacetime. Then we say that sigma is a photon sphere, provided the cylinder over sigma is a photon surface. Now so that's the definition. We're not assuming, just the terminology, we're not assuming that sigma a priori is a sphere, but it almost always has to be a sphere, topologically a sphere, as we'll discuss. And of course, the classical example is the R equals 3m sphere in Schwarzschild. So we have this notion of photon spheres within static spacetimes.
Is it the same as the previous definition?
Pardon?
Is it the same as the previous definition? So
It's got to be. So P is
yeah,
the
I mean, this
photon surface is any
space,
time-like hypersurface. Here we're taking a closed surface in M and looking at that standard cylinder over sigma and requiring that to be a photon
So
surface.
this is more restrictive. Than
More
this.
restrictive. More restrictive. It's a good point. It's relevant to some other things we've been looking at that I might mention towards the end. Right. So it's not any cylinder over sigma. It's this. Yeah.
The flow by the key
Yeah,
vector.
exactly. Now, in Carla's original work, she derives some relationships among various geometric properties that we need for our work as well. So these first properties and essentially local properties. And here's the setting. So we have our static space-time, which we assume satisfies the vacuum Einstein equation, which means that the static potential n satisfies these equations on M in the metric G. And let sigma be a photon sphere in N, so that means that cylinder over sigma is totally umbilical. Okay. Then using the vacuum Einstein equations together with the Gauss-Kadazzi equations for P within space-time M bar, Gauss-Kadazzi equations for sigma within P, and in fact sigma is totally geodesic within P, and the Gauss-Kadazzi equations for sigma within space M. So using all these, one establishes the following properties. This photon surface P over sigma must have constant mean curvature and constant scalar curvature, and the scalar curvature and mean curvature are related by that equation. Then let's go down to the photon sphere sigma in M. One shows that photon sphere must be totally umbilic and must have constant mean curvature. Then we come to some critical relationships here, which requires that sigma be an equipotential photon sphere. That is to say, it's a photon sphere along which n is constant. Now, we tried hard not to use this assumption, this condition, but we haven't succeeded in that. It's an open problem whether you can prove these rigidity results without that. On the other hand, the black hole uniqueness results, the horizon is also equipotential, namely n equals 0. So, assuming that sigma is an equipotential photon sphere, the Gaussian curvature of k of sigma and its mean curvature related by a there. In particular, sigma, our photon sphere, must have constant Gauss curvature. In particular, if the mean curvature is not 0, and it's going to be not 0, then k is constant. Sigma has constant Gauss curvature. And so sigma's orientable, and it's going to be orientable. Then, in fact, our photon sphere must be a round sphere. And then a second relationship holds, namely n along sigma n times h is twice the normal derivative of n. Both of those relationships are crucial to the proof.
Okay.
Yes?
So is there any code just to try to do this without assuming that the elapse is constant on this?
There's always hope.
But I mean, you've tried hard and it just...
We were hoping we could somehow, there were other conditions around where we could infer it.
But it's not.
There's an alternative characterization of a photon surface that will be helpful. In fact, it's used in our proof. So this alternative characterization, so let M bar G bar be a static space-time, and let sigma be a photon, then a closed surface sigma is a photon sphere in M, or in this static space-time, if and only if it's totally geodesic in M, not in the physical metric, but in the so-called Fermat metric or optical metric, which is conformally related to the physical metric by the factor n to the minus 2. So it's a fact that closed surface is a photon sphere if and only if it's totally geodesic in the so-called Fermat metric in M. That emphasizes again the special, how special photon spheres are, that they are totally geodesic within the Fermat metric. Yes?
So it's an equipotential?
No. Right. Does not assume equipotential. In fact, Gary Gibbons has studied photon spheres from this point of view. He has he's studied Fermat metrics in a large class of static spacetimes with various fields present, other dimensions, and so on. This characterization, in fact, is a consequence of this well-known second proposition here, which says you look at null geodesics in our static spacetime, the projection along the T lines into M are geodesics in the Fermat metric. So projections of null geodesics into space are natural projection are geodesics within M with respect to the Fermat metric when suitably parameterized. One can understand this fact as follows. You look at the paths of null geodesics in space-time or Lorentzian manifold. The paths of null geodesics are conformally invariant. In fact, there's a conformally invariant way of characterizing null geodesics. So if we have a null geodesic in our original physical space-time, then it's also a null geodesic in our space-time with this metric GF bar. But when we take the physical metric and multiply by n to the minus 2, this is the metric we get, minus dt squared plus the Fermat metric. But you see, this is an exact product. This is a product metric, and it's a simple fact that geodesics in a product metric project into geodesics into the factors. So we need this fact that photon spheres are totally geodesic in the Fermat metric. Now I want to consider some properties of photon spheres that are non-local. And again, this does not require equipotential. So for these non-local properties, here's the setup. Again, we have a static space-time that satisfies the vacuum Einstein equations. We assume that space is asymptotically flat for simplicity with one end, and that the boundary of M is a union of photon spheres, sigma j, which we know by local results or CMC that does not require potential. Then we have the following proposition that the mean curvature Hj of each photon sphere sigma j must actually be strictly positive with respect to the inward normal, interior normal, so that the photon spheres must be mean convex to the inside, to the interior. In fact, they're embellic, so they're convex. They're outer untrapped, if you will. And let me say a few words about the proof, which is kind of nice. So suppose to the contrary that for some j, the mean curvature of sigma j is less than or equal to 0. So we fix some notation. We let sigma stand for sigma j, and we let S be the union of all the other photon spheres that are present in the boundary. And then we take a large radial sphere, SR, out on the end. So here's a picture. Let V be the region bounded by the boundary of M and this large radial sphere. We're assuming sigma has non-positive mean curvature. And we go far enough out on the end so that radial sphere has positive mean curvature. And we're going to construct a flow locally around this curve gamma. Now, what is gamma? Well, gamma is sigma and SR are compact. So the distance between them is finite. So we let gamma be a unit speed, and I'm talking now about Fermat distance. This flow is constructing using the Fermat metric. We let gamma, defined on the interval 0 to L, be a unit speed geodesic in the Fermat metric, whose length realizes, so gamma is a Fermat geodesic whose length realizes the Fermat distance between sigma and SR. Now, the construction, this is a manifold with boundary. We're constructing a minimizer in this sense in the Fermat metric. The construction of gamma needs that S, which is a union of photon spheres, is totally geodesic. The fact that they're totally geodesic means when you construct gamma, it's not going to hit S. It's not going to be tangent to S or anything like that. So the construction of this length minimizing or realizing Fermat geodesic uses the fact that S is totally geodesic in the Fermat metric. So then we let WT be the set which is a constant distance t from gamma for all t between 0 and L. So let me move to the next slide. So WT is a constant distance t in the Fermat metric from sigma, and because of the length minimizing property of our Fermat geodesic gamma, there are no focal points on gamma to sigma t, and so that this WT is going to be smooth near the point gamma t. In fact, it's actually reached by flowing at unit speed in the Fermat metric per time t. And it will be smooth near gamma t because of the absence of focal points. One technicality is that the endpoint, so gamma goes from P to Q, the endpoint of gamma Q may not be ruled out as a focal point. That's a technical point, so we can, in fact, assume that Q is not a focal point either. So the final surface, T equals L WL, will also be smooth. Moreover, by the minimizing property of this gamma, that last slice WL will lie to the inside of SR. And so in fact, we have this smooth family. We have this flow localized around gamma, and each WT is obtained by flowing, say, at unit speed in the Fermat metric, but in fact, speed n in the physical metric. Now, because this WL lies to the inside of SR, and SR has strictly positive mean curvature, W sub L has positive mean curvature at Q. But then we run into a contradiction, because we let H of T, again, be the mean curvature of WT at the point gamma of T, so we have H as a function of T. Then it's a nice computation to show that you have a monotonicity formula, that the T derivative of H over N is less than or equal to 0. BT is the second fundamental form of WT at gamma of T. So you have this nice monotonicity formula, but this says that since sigma has non-positive mean curvature, then by this monotonicity formula, WL must have non-positive mean curvature, contradicting the fact that it actually has to have positive mean curvature. So anyway, that's the argument. So our photon spheres on the boundary must have positive mean curvature, just like R equals 3n.
But you're assuming that H is constant over this? Because what if H changes sign? I missed this part. The initial H.
So this is non-positive, we're assuming. And
but I mean, if H is not constant, it could be starting at a point where
we're just looking at H at each point along this gamma.
Oh,
so
I see.
just looking at H at each
so
point
you're
along
minimizing
this
distance not between the sets, but this point on the bottom.
Yeah,
Okay,
so
fine.
just looking at H of T at each gamma of T. Keep looking at my watch because 40 minutes. So this type of argument has further consequences. Let me just mention. We've assumed that M has only one asymptotically flat n. You can actually prove that it has, say in this vacuum case, it actually proves that you can actually prove that it only has one n. And here's the idea. So say here's the boundary, and say there were two n's, more than one n. Then you can run essentially the same kind of argument by choosing a Fermat minimizer. So you go way out on the ends, truncate. These both have positive mean curvature. Then you construct a Fermat minimizer between those two components on the end, and you run the same argument, you get a contradiction. So you can argue that M only has one asymptotically flat end. You don't you can do better than vacuum. In fact, this argument works as long as the static spacetime satisfies the null energy condition, reaching non-negative or null vectors. And this argument doesn't depend on dimension either. So these are some advantages of this argument. So in fact, you can argue that M can only have one asymptotically flat end, and this in turn implies that M must be simply connected. Because if M is not simply connected, you can pass to the universal cover, and since the ends are simply connected, they'll lift to more than one end, and you run the argument again, get a computation. So M must be simply connected. This is sort of a photon sphere space-time version of topological censorship or something like this. And then once M is simply connected, it's a purely topological fact that each component is a topological sphere. It can't be non-orientable. So our photon spheres, when they're equidifferential on the boundary, they've got to be genuine round spheres. So let's talk about now the proof of this uniqueness theorem. So here's the statement. We consider static space-time, M bar G bar, which obeys the vacuum Einstein equations. Static potential must satisfy these equations on mg. We assume that mg is asymptotically flat, one end, that n decays to 1 at an appropriate rate out on the end, and that the boundary of M consists of equipotential photon spheres. You may recall when I stated this in the beginning, I didn't include equipotential, because in fact in our original paper we made that part of the definition of a photon sphere. Then M bar G bar is isometric to the region R greater than or equal to 3M in Schwarzschild space-time.
Right? You're probably also assuming that n is strictly positive, right?
Well, of course, yes, strictly positive. As a stat, it's a proper static
Definition of
space-time.
static.
So then M bar G bar must be isometric to R greater than or equal to 3M in Schwarzschild space-time. In particular, the boundary is connected. There's only one photon. And the idea of the proof is quite simple. We're going to construct a static vacuum black hole space-time that extends our given space-time, and then apply the black hole uniqueness result of Bunting-Masood. So really, all the real work is in the proof of the Bunting-Masood black hole uniqueness result. So here's what we do. We start with mg, and for each photon sphere sigma g, we're going to glue in a Schwarzschild sigma j, we're going to glue in a Schwarzschild neck Vj. And this Schwarzschild neck, define it in a moment, this Schwarzschild neck extends down to Tj, which is just a horizon in Schwarzschild. So this gluing process requires all these general results about photon spheres that we've been discussing. So we let Kj and Aj be the Gauss curvature and mean curvature of the J photon sphere. We know that they're constant, and moreover, they're related in this manner. In particular, sigma j is a round sphere, and Kj is positive, this is positive, Kj is positive. Gauss curvature is a constant positive, that determines the radius. So sigma j is a round sphere with radius 1 over the square root of the Gauss curvature Kj. So now we're going to glue in at sigma j, we're going to glue in the Schwarzschild neck. It's just this interval across S2. How do we choose Vj? Well, it's a Schwarzschild neck. We just have to say what the mass is. And so the metric, this is the spatial Schwarzschild metric. Mu j is the mass. And we define mu j to be Rj over 3, so that Rj is 3 times mu j. So this goes from 2 mu j, where you have your horizon, Schwarzschild horizon, up to 3 mu j, which is Rj. Then you can check that if you look at this is mu j. You look at the top here of the neck. Look at the top here of the neck. It has radius Rj. It's a round sphere. So the induced metric of sigma j and the induced metric of the top of the Schwarzschild neck agree with the same induced metric. And moreover, you can use this relationship to show that mean curvatures agree, and because they're umbilic, totally umbilic, the second fundamental forms agree. So along the gluing surface, the induced metrics and second fundamental forms agree. So now we're going to construct this static vacuum black hole spacetime. So let m tilde be m with those necks attached, and we extend the metric g tilde to be g on m, and the Schwarzschild metric with the appropriate mass, gj on vj. And because at the gluing surfaces the induced metrics and second fundamental forms agree, you can introduce coordinates at Gaussian normal coordinates so that the metric g tilde is C11 across the gluing surfaces, smooth elsewhere. So we have our metric g tilde for this static black hole vacuum spacetime we're defining. Now we need our static potential. So our static potential on m tilde is n tilde, and it's equal to n on m, and it's equal to a constant times the Schwarzschild static potential on each Vj. Here, Nj is just the constant value of n on sigma j. Then again, using one of the earlier properties, relationships that I talked about in the local properties of photon spheres, you can show that the static potential n tilde is C11 across the gluing surface, and elsewhere is smooth and satisfies the vacuum static field equations. So in fact, we've constructed static spacetime m hat equals r cross n tilde with static metric g hat equals minus n tilde squared to t squared plus g tilde. This is a static black hole spacetime. The boundaries are just Schwarzschild horizons, and you can now apply Bunting-Massoud, the uniqueness result for static vacuum black hole spacetimes, to conclude that m hat g hat is Schwarzschild. And this actually gives the result. Now there's a little bit of a regularity issue because there's the C11ness across the gluing surface. Similar features arise in the proof of Bunting-Massoud. The proof of Bunting-Massoud makes use of the positive mass theorem, specifically the rigidity part of the positive mass theorem. And but we now know, I mean, this goes back to work of Bartnik, that the positive mass theorem, and in particular the rigidity part, holds in sufficiently low regularity that certainly applies to this C11 business across gluing across these surfaces. So the positive mass theorem applies, and basically then you get the result from the black hole uniqueness result of Bunting-Massoud.
Well, now there's this beautiful version by Lee and the plot.
Yeah, you need nothing.
You need nothing.
Nothing. C11 is like heaven in their result. Exactly. But in fact, the conditions in the original Bartnik, but like you say, Lee and the flock, under very weak regularity conditions, you get the positive mass. Any other questions or comments? Some generalizations. There's some obvious directions in which to generalize. One is to consider the non-vacuum case. Here we've been discussing only the vacuum case. Einstein-Maxwell case was handled by Izadjev and Lazov, adapting Carla's original Israel proof type argument, in particular assuming a single photon sphere. Carla and I have written a paper where we use this other method to handle the case of multiple photon spheres. Izadjev has done the Einstein scalar field case. There's a recent paper by Rogatku on the archive, which looks at Einstein-Maxwell dilaton. I haven't looked very carefully at that case. So you can derive these non-vacuum of static spacetimes with photon spheres. Another natural generalization is to consider higher dimensions. And in fact, Carl has obtained a very nice generalization of this uniqueness result to higher photons, with the conclusion being that it's Tangerini Schwarzschild, which is the higher dimension version of Schwarzschild. Some further generalizations. So let me just make a comment here. When Carl and I started talking at MSRI and then later, in fact, at other meetings, we weren't just interested in behavior of photon spheres, but also photon surfaces in general. Remember, photon surfaces are defined, you don't have to be in a static space-time. Photon surfaces are just time-like hypersurfaces, which are totally invariant. And we were interested in the occurrence of photon surfaces. Now, of course, there are many photon surfaces in Minkowski space, as I indicated at the beginning, and so one would expect, since Schwarzschild spacetime is asymptotically Minkowskian, that there should be plenty of photon surfaces within Schwarzschild. And what distinguishes the special R equals 3m photon surface? And in fact, we've constructed all sorts of foliations. So this is just a schematic diagram. So here's R equals 2m, the horizon. Looking in Schwarzschild specifically, here's R equals 3m, and then we go out to infinity. So this is in space-time now. And here's the R equals 3m photon sphere cross R, photon surface. And then for R greater than 3m, there are also photon surfaces. And in fact, R greater than 3m is foliated by photon surfaces, which extend out to scry. And for the region between 2m and 3m, this region is also foliated by photon surfaces. It looks sort of like this. So in fact, the entire region R greater than 2m is foliated by spherically symmetric photon surfaces. What distinguishes the photon sphere is that it's bounded away from scry and bounded away from the horizon. And that seems to be the unique choice. So anyway, we often wondered whether we could get away a little bit from requiring that our static spacetime have a photon sphere where we're looking at this exact cylinder generated by the T-lines over the surface. And so we have considered the following situation. We introduce what we call equipotential photon surfaces. And these are photon surfaces within equipotential photon surfaces are photon surfaces within a static spacetime, such that when you look at every T-slice, it intersects in a compact surface along which n is constant. So the n varies along the T surfaces, but is constant within each T surface. So we're still doing a little checking some details, but it appears that we can get a uniqueness result for equipotential photon surfaces. And then there's the stationary case, which I think is quite interesting, potentially interesting. Kerr doesn't have any photon surfaces, but it certainly has this region of bounded photon trajectories, bounded null geodesics. So there's a region there. It has some structure. I haven't really come to understand that structure yet, but it has some structure. So one would like to sort of understand the structure of this bounded photon region within Kerr to somehow then, if you come up with the right characterization of that region, prove, say, a rigidity result for Kerr instead of Schwarzschild in the stationary case.
So is this completely clear that there are no photon surfaces at all?
I guess I'm not I don't believe so. Okay, so I haven't checked that. I'm not absolutely certain, but I don't believe so.
Because one knows that there are trajectories which are trapped, which are not of constant radius, but maybe there's a way of putting them together so that they would form a...
Maybe, but I don't think so, but maybe. But anyway, there is a structure there, as you point out. There is a structure there, and you'd like to try to capture it. And it can't be a photon surface in the way we mean, otherwise it's got to be, well, a stationary metric, so I guess. But I suspect if there were a photon surface there, it would probably force it to be short-shielded, but I don't know. But anyway, it'd be nice to understand that structure and get some rigidity result with the conclusion being curved.
They were non-smooth. The interior is not saying it's smooth. Both sides is non-smooth.
Pardon?
I said, if it exists at all, it may be very non-smooth.
I see what you're saying. Anyway, so that's the end of my talk. Thank you very much.
What about non-spherically symmetric photon sphere in Schwarzschild? Because this would be somehow related to the calculus.
In Schwarzschild, I believe
They have to
that
be-
we've checked, we've ruled those out. They don't
They
exist,
have-
except for some special planes or something like that. With compact cross sections, I think you only get the spherical symmetry.
Do you think that, so you said over here that photon spheres were kind of characterized by the fact that they're bounded away from r equals 2m in Scri, right?
Yes.
Do you think that this is a possible way to generalize photon spheres away from static spacetimes?
By assuming that they're making this boundedness assumption.
Uh-huh.
So this was one of our original thoughts when we started talking about it, and it's a nice idea. Haven't made any further progress with that.
Other questions?
Let me take that back. If I'm sorry. So we have one argument. If you have this, if you have a photon surface, maybe in this equipotential case, that's bounded away from the horizon and bounded away from Scri, at least in one direction with one of these photon surfaces, then you can show under certain circumstances that you get the limit, and then the limit has to be limit in a certain sense has to be a photon sphere, and then the uniqueness result kicks in. So a bounded one somehow should lead to a photon sphere in the sense we discussed, and then so that's one thing.
Interesting.
Any more questions? When is the second part?
At 45, so we probably have a few minutes. 5 minutes.
5 minutes. Okay, thank you.